Hello friends, in this video I'm going to show you how to draw the Lewis structures of covalent molecules or compounds. Recall in the last video we used Lewis symbols and Lewis structure to illustrate the formation of ionic compounds. In this video we're going to show you how covalent bonds are formed, and we're going to use Lewis structure to explain that. Nice. So permit me now to say that Lewis structures are drawings that help us to describe the bonding in covalent molecules and also bonding in what we call polyatomic ions. Recall we said that polyatomic ions are ions that comprises of more than one element, two or more elements. Okay? Nice. So, example of Lewis structure depicted in the formation of covalent molecules or compound. The first and easy peasy example is the formation of chlorine gas or chlorine molecule from two atoms of chlorine. If you recall the Lewis symbol of chlorine, you understand it has 7 electrons, in the Lewis symbol. All right? So when two atoms of chlorine come together, they share each of their valence electron. And that sharing, creates what we call a shared pair. When this chlorine atom brings one electron, and this chlorine atom brings one electron, they come close enough and they share those two electrons. The idea is for both of them to become stable by attaining the noble gas electronic configuration. Nice. These two electrons that we have shared were used to make what we call a covalent bond. And those two electrons are called the shared pair or shared pair of electrons. But if you look at the anatomy very closely of the chlorine atoms ab initio, you discover that in this molecule it has a pair of electrons that was not involved in the chemical bonding. There is another pair of electrons in this atom not involved in the chemical bonding. You also have another pair of electrons that never took part in this chemical bonding. These electrons are known as lone pair of electrons. Lone pair of electrons, or you call them non-bonding electrons, because they were not involved in the sharing or the covalent bond formation. So you discover that this electron and this pair of electron and this pair of electron are called 3 lone pairs of electrons. They are non-bonding electrons pair because they are not involved in the covalent bond. But these two that were involved in the covalent bond are known as shared pair of electrons. So for this atom, you can agree we have 3 lone pairs of electrons. While for this particular atom, the second chlorine atom that made this molecule, we also have 1, 2, 3 non-bonding or lone pair of pairs of electrons. Okay? So why the 2 electrons bounding the 2 atoms in that molecule is called the shared pair. The shared pair, or you call it the bonding pair. Okay? Shared pair of electrons, or you call it the bonding pair of electrons. Nice. So when the Lewis diagram or the Lewis structure of a molecule has been drawn, it is conventional for us to replace the shared pair, those 2 electron pair, or the electron pair that was used to make that covalent bond, is usually conventionally replaced using a dash or a line to give us a preferred Lewis structure. For instance, in the case of hydrogen molecules, Two atoms of hydrogen brings each of their valence electron. Those two electrons, remember, are called the shared pair. So these two are known as the shared pair or the bonding pair. Okay? At the end of the day, the shared pair or the bonding pair, these two electrons or the shared pair is conventionally usually replaced with a dash to give a preferred Lewis structure. Okay? Just as we did in the last illustration, the formation of chlorine molecule, you can see the shared pair, okay, now being replaced with a dash. The idea ultimately here is that the shared pair of electron gives us what we call a single covalent bond. If we have one shared pair forming the covalent bond, we're expecting to have one single covalent bond. If we have two of the bonding elements bringing two electrons each, that means we have two shared pair. Therefore, we are likely going to have double covalent bond. In some instances, we have two elements that are forming covalent bond with each supplying to the mix or bringing 3 electrons each. Therefore, we are going to have 3 shared pair in such molecules. And eventually, we are likely going to have 3 covalent bonds in the process. Going forward, I'm going to show you examples of covalent molecules that were made to have double and triple covalent bond. But for now, we're going to still pay attention to understanding the essence of the bond formation or the essence of the rearrangements in the valence electrons to form a given covalent molecule. That leads me to what we call the octet rule. So recall that chlorine belongs to group 17 in the periodic table, a group that has a unique name called halogens. All of these elements can join up to atom of the same element to make diatomic gases. In this case, chlorine and chlorine combine to make Cl2, which is chlorine gas, with the formation of a single bond, which ultimately helped each of the combining atoms to acquire the octet structure or the noble gas electron configuration. At the end of the day, in every single bond, we have 2 electrons. So if you check it, we have 2 electrons for the both chlorine atoms. 2 plus 2 is 4, plus this is 6, plus this is 8. At the end of the day, this atom is stable, having acquired the noble gas electron configuration of 8 valence electron. This particular bond, again, is 2 electrons also for this atom. So you have 2, 4, 6, 8. At the end of the day, you have 8, total of 8 electrons in the valence shell. So same way that chlorine atom can react or combine with another chlorine atom to make chlorine gas, all other members of the halogen family react with each other the same way to make diatomic molecules too. Example is what we call fluorine gas, bromine gas, iodine gas. All of these will form covalent bond, a single covalent bond between itself, okay? At the end of the day, they are going to have 3 lone pairs of electrons left in each of the atoms in the molecule. Nice. This is fundamental for us to understand. If you check at the end of the day, all of the atoms involved in this bond acquires 8 electrons in their valence shell and are said to be stable, just like the noble gases. Nice. So this formation of single covalent bond allows each of these halogen, fluorine gas, bromine gas, iodine gas to have what we call the noble gas electron configuration. Just like I said, Each atom now has 8 valence electrons. When you come to the periodic table, you will discover that elements in the periodic table are placed into special classifications or groups. We have what we call the main group elements, also known as the representative elements. Of course, these are elements that are said that their electron configuration ends with either in the s orbital or in the p orbital. Example of such elements are elements you find in group 1, group 2, group 13 until group 18. These elements are also said to be placed in the S and P block of the periodic table. All of these elements would react with itself or other elements just to ensure that each of its atoms acquires 8 valence electrons in the outermost shell. Suffice it to say that elements in group 1, group 2, and group 3 are predominantly metals, in which case they will lose some of their valence electrons, if not all, to become stable or to acquire 8 electrons in the valence shell. We use the Lewis structure to depict this. Suffice it to also say that elements in group 14, 15, 16, and 17 are usually non-metals. Hence, they will have gain electrons, usually from the metals in a redox reaction, in order to acquire their octets. Okay? And again, we can use Lewis structures to depict all of this. So elements in the S and P blocks of the periodic table, also known as main group elements or representative elements, they all have the tendency of forming covalent bonds or chemical bonds, okay, in order to obtain 8 valence electrons. And this is known as the octet rule. So the octet rule simply tells us that main group elements or representative elements are going to undergo chemical reactions to form chemical bonds, either ionic or covalent, in order to get to their octet electron configuration or octet structure. And that is what we call the octet rule. All right? Besides the main group element, we also have elements, specialized elements in the periodic table. The elements lying between group 2 and group 3 are special elements called transition elements or transition metals. I'm going to dedicate a lecture, a video or series of video lectures just talking about transition elements, talking about their characteristics, talking about how they're used in making coordination compounds and how they are involved in catalysis and formation of colored compounds. But for today, we need you to understand that when main group elements or representative elements form chemical bonds, okay, be it ionic or covalent bonds, they are able to obey the octet rule for all of the atoms in the reaction to be stable or acquire the octet rule or octet structure. Again, it is important to note at this juncture that the number of bonds an atom can form can be predicted from the number of electrons needed to reach the octet. Again, the number of a chemical bond or a covalent bond that an atom can form can be predicted or can be deduced by merely counting the number of electrons needed for it to become electronically stable or for it to obey or reach the octet structure. Nice. And this statement is especially true for mostly non-metals such as carbon, nitrogen, oxygen, fluorine, and so on and so forth. If we decide to take carbon, for instance, as an example, to appreciate this statement, you understand that the Lewis symbol of carbon is carbon centrally placed with 4 dots representing the Lewis symbol of carbon. Understand that carbon has 4 valence electrons. Therefore, for it to acquire 8 electrons in that valence shell, carbon requires 4 more electrons. So here, we gave you that the valence electrons present in carbon is 4. And it needs or requires 4 more electrons to fill or attain or reach the 8th octet. Remember, we just said that the number of electrons required to reach octet for a given non-metal or even a metal tells us, for a given non-metal tells us the number of possible covalent bonds it will make. So because carbon requires 4 electrons to reach octet, we are expecting that carbon will always have 4 bonds going out of it. That is why you have carbon making 4 bonds. This particular statement helps us to understand the tetravalency of carbon. For instance, in carbon tetrachloride, you can see that carbon, which is least electronegative than chlorine, is centrally placed, and you have 4 chlorine atoms surrounding it, and all of these are depicted using their Lewis symbols, and you see the 4 covalent bonds that are formed. In the next video, I'm going to proceed to showing you the rules that we must follow if we must draw the Lewis structure of complex molecules. Again, here we started with drawing Lewis structures of simple molecule like chlorine molecule or chlorine gas, traveling towards carbon tetrachloride. We're going to draw even more complex molecules. But for us to draw those Lewis structures properly or appropriately, there are set rules that we must follow. So in the next lecture, in the next video, I'm going to itemize the rules that we must follow if we must depict the Lewis structures of complex covalent molecules. I don't know if you learned anything from this lecture. Please kindly like, love, comment, and share so that this video can get to those students who needs it and who may wish to appreciate this particular topic. The way topics in chemistry are structured is that if you don't understand A, when you get to B, you might be a bit confused. That is why I'm taking my time to teach you these topics in a series which I take gradually. I take it from A to B to C and so on and so forth in that manner. So again, if you enjoyed what we just did and you are anticipating for more, kindly like, love, make your comment and share. The next video will thrill you even more. Thank you. Stay safe. Bye.